Start the new section today, which is on queuing theory, and it sort of gets a bit more mathematical at this stage, and so it'll start a little bit simpler today, and then progressively it gets a bit harder. Okay, so I'm just going to start very simply with queuing theory. What is it? And then we'll go over a very simple, intuitive but powerful result called Little's law. And then we'll talk about the basis of queuing theory, which is stochastic processes, explain what it is, some types of stochastic processes, and we'll focus on a specific type of stochastic process called a Markov process, try to explain why it's important, and hopefully you'll understand Markov processes pretty well by the end of this. And then if I have time, I should be able to do homogeneous Markov processes, and most likely I won't be able to get to the Chapman-Kolmogorov equations. If I can, I will, otherwise we'll continue with that on Thursday. All right, so what is a queue? What is queuing theory, generally speaking? So queue is, it presupposes two entities, a server and a client or a customer. And we represent servers like this, and we actually don't represent clients. What we do represent is a queue, which is drawn like this, with essentially a place where customers can wait. And in the simplest case, you can think about it, is, for example, you go to the Tim Hortons, and that's the longest queue you see around here. And there's a service person who is servicing a request. That's the Tim Hortons service person. And this is the corridor where everybody's sitting, and of course you're the customers. Now, what happens, right? Let's imagine the following situation. Let's say there was no queue, all right? So you go to Tim Hortons, and either you can get service right away, or they say, well, go away. Essentially, there's no space. So there's one person who's being served. Perhaps you can represent it like that. Not in the queue, being served at this point. And then if that person is busy and they go to the queue, you're just thrown out. You can't go in. And this is not as silly as it sounds. Imagine a plane now, right? You don't have a queue of people waiting to get onto an available plane. You have a reservation, you get in the plane. If you're in the plane, you're being served. And if you go to the plane and there's no space, well, you're not being served. There's no queue per se. It just is or is not. We are not interested in plane-like situations. We're interested in queue-like situations where there is a server and there's a customer. Now, one of the things you need to understand about queues is that queues go with buffers. There is a storage space. This is called the queue or the buffer. And what's being stored in here are service requests. Or in some cases, it's customers, but more generally, when we talk about computer systems, we're talking about service requests that are being stored over here. Now, what you have to realize, and this is just common sense, you don't need queuing theory for this, is that let us say that the service rate over here is intrinsically some rate of service. We draw that represented always as mu. That's called the service rate. And correspondingly, we have a rate at which customers enter the system called the arrival rate. And we represent this as lambda. The intuitive and obvious observation is that mu has to be greater than lambda, or at least greater than equal to lambda. And this is, as I said, you don't even need queuing theory for this. This is just obvious common sense. Why? Because if mu is smaller than lambda, then there's always going to be more people arriving than can get served. So this queue is going to become infinitely long over time. And so we call that system unstable. Okay, it's an unstable system when the service rate exceeds the arrival, the arrival rate exceeds the service rate. Okay, so we don't want to discuss unstable systems. We're really talking about stable systems where lambda is less than mu. And later on, we'll see actually a proof of stability, etc., where lambda is less than mu. But this is just common sense. You don't really need you don't need to be very smart to see that happening at all. So that's the first observation I want to make over here. The second observation I want to make over here is, again, this is something that's not in the lecture notes. Probably I should put it in. But in computer networks, what is the role of buffers, right? So we automatically assume, at least we meaning the networking type people, assume that all routers and switches and service elements such as those have a buffer with them. What is the buffer for? The buffer is basically only to deal with transient overload. Okay? In other words, what a buffer does is that there is a mismatch between the arrival and the service rate. The arrival rate is less than the service rate. You have to remember that it's not the case that the buffer is there because the arrival rate is greater than the service rate. No, the arrival rate on average is guaranteed to be lower than the service rate. Okay? However, there are some periods of time where the arrival rate and the service rate are out of whack. Okay? For example, let's take a practical example over here. You go to Tim Hortons. In general, the arrival rate is less than service rate, right? It's obviously the case that the queues are not going on to infinity, right? What's going on is that there are bursts of arrivals. There are periods of time when a bunch of people come. So class ends, everybody wants to go get a cup of coffee. They all arrive to the queue, to the server, essentially at the same time, and then they all get stuck in the buffer, and then they get served, and then the queue disappears. Okay, so we have this, situation where the arrival rate and service rate are temporarily out of whack. If we were to draw a figure like this, time on this axis, we can think of the service rate as being something like this. I'm just, ignore the y-axis for now. And what we're seeing here is that, or maybe I should draw it the other way. So this is the service rate. In some sense, the service rate has some mean like this, and the arrival rate has got some mean like that. And for some period of time, service rate is below the arrival rate. Okay, so or potentially the arrival rate is much higher. I guess what am I doing over here? This is the other way around. The arrival rate over here is higher than the service rate. It's higher over here. I need different colors to do this properly, and out of colors. Let me draw this once more. And let's see. So that's the mean. I want to make this a mean arrival rate. And I want to make this the mean service rate. So that's above. And let's say this has some variation over this. And what I'm basically saying there are periods of time, like this section over here, where the arrival rate exceeds the service rate. Okay. Similarly, this section over here. Notice it goes below the mean as well. It's just that, you had these temporary glitches over here. Same thing over here. So these three periods are periods where the arrival rate temporarily exceeds the service rate. I want to focus on the fact that it's a transient overload. It is not persistent overload because persistent overload is not stable. Okay? So queuing theory focuses on this specific phenomenon, the transient overload phenomenon, that allows us to compute certain metrics of interest about this transient phenomenon. Again, some of you came in late, so I just want to emphasize this because this is where you can go wrong. If you don't have the right foundation, you can just go wrong. The purpose of buffers is not to deal with persistent overload. You will never, ever solve persistent overloads. Okay? First point. Second point, transient overloads happen because the arrival rate, which is this instantaneous arrival rate, exceeds instantaneous service rate. So queuing is by definition a transient phenomenon. Okay? And third, queuing theory is looking at the behavior of this transient phenomenon. All right? And so if you have a persistent overload, the only way out of that is to increase capacity or decrease demand. So how do you increase capacity? You bring on more servers into Tim Hortons. If you decrease demand, how you do that? You basically throw people out, or you raise the price of coffee, and then people won't drink as much coffee, and then the demand goes down. Or we have what are called discouraged customers. They see the queues long and say, I don't think I want coffee anymore. I'd rather just go, I'd rather not do this, right? So we have discouraged arrivals, and then what happens? Arrival rate kind of goes down because we have discouraged arrivals. We will study some of these phenomena, not all of them further on, but I just want to get this point across, very, very strong, that we're studying transient overload. Okay? Any questions about this so far? Okay. All right, so because most queuing theory textbooks and most queuing theory analysis and everything acts as if queuing is always going to be there. No, it's just a temporary thing. It may dissipate in milliseconds or microseconds or seconds. It's not going to last very long. We don't want it to last very long. In some sense, queuing already is a bad thing. Okay, you don't want to have queues. Okay, so if some router vendor comes to you and says, I have a gigabyte of buffering in my switch, I'm a great switch. You're saying, why? You're catering to a phenomenon that should not exist. That means the service rate is so bad that you need to put lots of buffers to accommodate the variations and arrivals. Okay, I mean, I'm being a bit facetious here. There's a very, very interesting ongoing debate on what is the right amount of buffers for switches, and I'm selling it way short with these remarks here. But the point I want to get across is just that it's transient. Okay, let me give you some examples of queuing in the networking world. So, as I said, switches have buffers. The normal way to represent a switch, this is if you have, let's say, let's do a simple two-port switch, because I don't want to draw too much. So how do you draw a two-port switch? You have two input ports, you have two output ports. Now, of course, the input and the output ports are the same thing, right? We just kind of open it up to make it easier to draw. And typically what we have is that, so we have two network interface cards. We have an input queue over here and a little server, and we have an output queue over here with its servers. And then we have some cross connect, which is drawn typically like this, like a X, and we draw this cross connect over here. And well, here we have 4 queues. We have 4 queues because stuff comes in the link, it gets stored in this buffer awaiting service, and then at some point the cross connect fabric says, okay, I have space, I can transfer something to the input. It goes to the input to the output, it goes and sticks in another queue over here, and it waits for the link to be free, and then off it goes. So we have, in fact, 4 queues in a typical 2x2 switch. Of course, if you have an 8x8 switch, you have 16 queues. So if you have you have n inputs and m inputs and m outputs, you have 2m queues, and you have fabric. If the fabric is buffered, then you have more queues inside the fabric. So switches and routers tend to be real fertile grounds for queuing theory, because obviously there's a lot of queuing going on. So that's one practical example. In fact, this is an example that motivated quite a bit of research in queuing theory. So the queuing theory started out as being part of logistics and operations research in the 40s and 50s, I guess, when people were trying to look at transshipment of goods and, and logistics operations in wars. But with the development of network processors and routers, queuing theory now is essentially dominated by computer-type people and networking-type people. Okay, the second kind of system where you can have a setup like this is, a typical web server. So we have a web server, and when we have, how does it look like? We have some kind of storage which has some content in it, and we're trying to load and store content, and then we have a set of machines, and we have a large set of machines. We have the internet, and then all of these guys are making requests to the web server. Typically, the web server will have a buffer where it's waiting for incoming requests, and it fetches a request, and off it goes. That's another queue. Again, the analysis of this system is quite interesting, and in just about 15, 20 minutes from now, we'll look at some numerical example for precisely this kind of web server. Okay. Finally, a system that has been studied a lot is the phone system, and here we don't have requests that are computers, but they're coming from phones. Now, forever and ever, phones are represented in this fashion, right? And actually, I don't even know if people of your age have even seen phones that look like this, right? A traditional, like a base with this big plastic thing that you hold in your hand. My kids have never seen a phone like this in their whole life, actually. For them, they're just used to cordless phones, and no doubt 10 years from now, kids will say, you mean you have a phone wire? What is that phone jack for? I don't know what it's for. Because they'll all have cell phones probably implanted in their brain or something like that. Nevertheless, all of us older people who remember this stuff draw phones like this. It's this traditional black base. You can only get one color, it's black. And handset on top. So I'll draw that. So essentially, these guys are connected to what's called a switch. And what you do is Oh, I forgot the little dials. Dialing a number, whoever thought of that? I mean, you can't just speak into your phone and have it call? It's like, wow. Anyway, so you pick up the thing and you dial this number, and what happens is it goes into what's called the call processor at your local central office. And what's going on is it's a request to make a connection to some destination. Of course, multiple people may be making calls at the same time, and we want to look at the queue of requests. In the modern age, the corresponding phenomenon is this. You leave the class, all of you want to call your friends, you all flip open your cell phone, and you say, you speak, or you dial the number, or whatever it is, or FEEP, the correct term is FEEPing the number in. I bet you didn't know that. Because when you press this keypad, what you send out is a frequency pulse. So the accurate technical term for pressing a number on your keypad is FEEPing. And, so you do this, and you get a busy signal. You say, oh, the cell is overloaded. Same thing, call processor tries to make multiple calls, and so we have an overload of arrivals. And when the arrivals overloads the service rate, the number of calls that can be carried in that particular cell, you get a denial of service, or in this case, a denial of service, or you have to wait for a while for your call to go through. You can have a fairly long time, it can be several tens of seconds, and that is nothing more than a transient overload under queue. So I'm just giving you some examples of queuing system just to kind of get your head around this over here. Okay? Any questions about this? Beg your pardon?
This is not a queuing system.
Why is it not a queuing system?
Isn't it like kind of the airplane example? If you can't get in, you have to get out and wait?
No, there is a sort of a set of, you can hold calls for a certain duration of time before you say, okay, it's busy. Yes, you're right. I mean, you can build it which has no queues. If you're incoming service request, you just say deny service if there's no available request. But you can hold it for a few seconds. Hopefully somebody's finished the call. It's a better thing to hold it for a few seconds than to immediately say no. So, yeah. So yes, so you can build it that way. Any queuing system can be built with zero buffers, right? And then you can say, okay, this is a reservation-only system. But you do actually have a little bit of capacity in there. It's good customer services to have the call go through, even if you have to wait 10 seconds then to send them a busy signal right away. I beg your pardon? You can get a call back, yeah. Yeah, you can get a send request and that will go to some other process and then it will call you back or whatever. There are many, many things you can do, but okay, we don't want to go on that. There's extra cost for everything. That's where the phone network works. Okay, so while we have this here, now we want to start looking at some metrics of interest. So let me just write down some metrics. So first metric could be, for example, the queuing delay. This is so what we do is we take this queue, well, we'll take this queue over here, and let's say the customer enters at some point, we mark it, we'll paint it red, and then we just wait how long before the customer exits the system, that same mark tag exits the system. That is called the queuing delay. Okay, so it's obvious. The second thing is the backlog. It's the mean number of, basically that's a mean queue length. Okay. So what is the mean queue length, right? And of course, what I was saying earlier was that when you have the lambda greater than mu, then you have an infinite backlog. Okay, it's an unstable system. Third thing is the fraction of time the server is busy. And this is also called the utilization. And again, for obvious reasons, you want the utilization to be less than 1. And we have the drop rate. In other words, how often does a customer or a service request arrive when the queue is full? Okay, if the queue has finite capacity. Now, we also study infinite capacity queues, but for finite capacity, we can look at the drop rate. And finally, we can look at the mean busy period. In other words, given that the queue is busy, how long did the busy period last? Okay, and one sign that things are going bad is that the mean busy period is growing over time. If I'm measuring the busy period of a switch or some server, and I find the busy period is keep on going up, then I have a pretty good sense that my queues need to be, managed better. Okay, so that's one good indicator. All right. So it turns out that we can compute these metrics. So it's the good news. We can compute these metrics, even though it's a transient phenomenon, and it can be fairly tricky to analyze. The good news is we can analyze them, but there's a big bad news. The big bad news is we can only analyze them when the arrival patterns are mathematically nice, or more precisely, when they're Poisson. Okay. So what does the Poisson mean? The Poisson means that the number of arrivals in a certain time period follows the distribution e to the minus lambda, lambda to the n by n factorial, so standard Poisson distribution. So we want the inputs to be Poisson, and if the inputs are Poisson, then we will give you all the metrics, all right? But the inputs are not Poisson, then we know less. And if the service rate is not what's called exponential, I'll come to that later, we know even less. So the general queuing system, which is essentially not characterizable. Okay, we can give very, very weak characterizations of the general queuing system. Okay, in fact, almost the only thing we know is Little's law, which we'll come to in just about a few minutes from now. But other than Little's law, there's very, very little we know about general queuing systems. So good news is we can give you metrics. We can compute these things. Bad news is input has to be Poisson. And it has been shown, as I mentioned earlier, that in fact traffic is not Poisson. So why are we studying queuing theory? What's the whole point? Okay. So the two good reasons for doing this. The first thing is that understanding queuing theory from a mathematical perspective, even assuming Poisson inputs, gives you intuition, gives you insights. Okay, you kind of get a feel for how these queues are going to behave, how these things are going to be put together. Okay, and as people working in the area of networking, as people who are working in the area of not even if you're networking, but anything that uses stochastic processes, it's good to have this intuition. Intuition is worth a lot. The second reason why it's good is that you can get numbers out of it. The numbers may not be completely correct, but they're sort of within an order of magnitude correct. Okay, so you cannot use queuing theory or queuing theory as we know it today to say, well, the airport lounge should have exactly 50 seats or whatever it is, right? Or the buffer size should be exactly this. No, it will say, according to Poisson arrivals and so on, the buffer size should be, let's say, 50 seats. That means that if you put in like 75, it's okay. You don't need 500. You don't need 5,000. So it's sort of ballpark, order of magnitude kind of stuff. And it's very good for that. So for these two good reasons, it's worth studying. Now, I should also mention that when I was going to grad school, I did my PhD at Berkeley, there was sort of this sentiment that you don't need to study queuing theory because who cares? At least in the computer science department, we were not encouraged to study queuing theory, and there was not even a course offered in queuing theory. And I had this attitude for many years afterwards that who needs queuing theory? And when I wrote a textbook 12 years ago, I basically stated in the book, who cares? We don't need queuing theory because all the assumptions are wrong. And I've had to change my perspective 180 degrees because I now have come to realize that even though everything I said there was true, yes, all the models are wrong, and we know it, yet the amount of intuition you gain is well worth the effort. And it is quite a bit of effort. It's not easy, it's not straightforward. We're going to make it as easy as possible, but queuing theory is hard work, but I think it's worth it because of these two reasons. Okay? Any questions at all about this? Yeah. Okay, so okay, let's start. So that's queues and kind of a high-level view of queuing. Let's start with Little's law. All right, and I'm going to leave this up because I'll need that. So Little's law was this law stated back in 1951 by J.D.C. Little, and it's a law that's so simple you don't need any maths to write it. You can just write it like this. You can say, and let me make sure I'm using the right terminology, mean number of customers in any queuing system, okay, is equal to the product of the mean waiting time times the mean arrival rate. and that's it. So I can tell you that the mean number of customers is a product of these two quantities. So let's see what it means intuitively. So mean waiting time is the amount of time you're spending waiting in a queue. So you go to Tim Hortons, you sit there, you wait in line for 20 minutes or whatever it is, or 5 minutes. That's a mean waiting time. That's your waiting time, and the mean waiting time is this waiting time across all customers. And then here the mean arrival rate, the rate at which people join the system. And if you multiply these two, you'll actually find out how long the queue is on average. So some people find it very intuitive. It's obvious. Why is it obvious? Well, you pick any particular guy coming in and you paint that person red and they join the queue. Okay, this is some person chosen at random. That person is going to wait so much time to get to the end of the queue, right? And in that time, how many people came? These many people came, right? Multiplied with this time is the number. And so that's how the queue is going to be, right? So that's pretty intuitive. And so some people find it intuitive. At the same time, it's also considered fairly deep result because it holds true no matter what the arrival pattern is. Okay, I don't care what the actual pattern of arrivals is. In fact, I don't even care what the actual service rate is. Okay, the services can be, you might not say that the people are served first come, first served. You can say, okay, we're going to skip the first guy, pick the second guy, then the fifth guy, we're going to serve all the alternate people, first all the odd people and the even people, whatever. You can say serve all the tall people first, and then the medium height, and then the short people. And serve in order of height. It doesn't matter, okay? It doesn't matter. You can serve it any order you want. People arrive in any order they want. Yet, this relation holds true because, we've got this waiting time sort of encapsulates all of the variations in service. Okay, the mean waiting time averages across all possible variations in service, and the mean arrival rate averages across all possible variations in arrivals. So the system, this equation is essentially insensitive to these two things, which is wonderful. And so this is pretty much all we know about general queues. Okay, this is a sum total of knowledge after 60 years of work about general queues, without knowing much more about arrival rates and the, first and second and third moments of their distributions and so on and so forth. Is pretty much all you can say over here. And it actually is useful. So let me first put a little bit of notation just so that it makes it easier for me to write. So I'm going to denote the mean waiting time as t, and I already said the mean arrival rate is lambda, and we'll call this as n, the mean number of customers, and we can just write that n equals t lambda. Okay. So let me do one example, and then we'll take a break, and then we'll do another example so that we're not going to be too far off in the example. So the example I have is something that you probably are used to, which is you get email all the time. You're sitting there, and email keeps pouring in. I get roughly about between 60 and 100 messages a day, every day. Okay, and these are non-spam messages. Okay, the amount of spam messages I get, I don't even know because they get filtered out. So they're lost. I'm getting 60 to 100. So I guess, or let's say you get 12 messages an hour, which is not too bad. Okay, well, it's about 100 messages a day, assuming that you have an 8-hour working day. 12 messages an hour is about right. And I'm saying that you read your mail once an hour. There's actually a little bit of time management advice hidden in this example, which is that people have found that if you are in the habit of checking your email as soon as it arrives, or worse, kind of hitting, get send and receive, or whatever the equivalent is in your reader, and you read mail all the time, it's equivalent to somebody knocking on your door, okay, 12 times an hour, saying, here I am, help me. Here I am, help me. Every 5 minutes, somebody's going to come and knock on your door. The time it takes for you to context switch your short-term memory out and swap in the corresponding whatever information you need to handle messages can take you up to 5 to 10 minutes, depending on how fast your context switch time is. Okay, so let's say it takes you 5 minutes of time to change context, answer the email, and change back. You are essentially doing no work. Okay, you're just doing context switching back and forth, back and forth. At the end of the day, you say, great, I was very productive at work. I answered 60, whatever it is, 100 email messages. But you know what? You got no work done. In particular, you did not do the homework for this course. Okay, so the answer, what you really should be doing is read mail once an hour, because you context switch once, and then you handle all your email, and then you shut it down. And ever since I did this, I refuse to read email faster than once an hour. My productivity has gone up. That is why I can write this book. Okay, so anyway, let's go back to Little's law. And what you're saying is that what is the average time a message is unread? Okay, now it turns out that this one you can solve quite intuitively, but let's just use Little law anyway. All right, so we have 12 messages an hour, so our mean message arrival rate is 12. In fact, it is deterministic because it's so 12 an hour is my arrival rate, and I read mail once an hour. If I read mail once an hour, then I know that the actually the question should be yeah, okay. So the mean number of unread messages, okay, is what? Okay, so I'm going to be getting 12 an hour, and then I have to sit and wait roughly half an hour. So the mean number of customers, which is the mean queue length, okay, is going to be 6. Okay? Why is that? Because you can imagine that this is 1 hour, and I have these 12 things coming in, okay? So the average, okay, is essentially what happens in this time over here, okay? So I'm going to have 6 waiting in the queue on average, the mean length of the queue. I'm going to have 12 waiting for me, but the mean length of the queue is basically 6. Why? Is because if you want to draw it this way, this is time, this is number of messages, and it goes up linearly from whatever 0 to 12. So the mean obviously is going to be 6. So mean number of customers is 6, right? And so I'm going to ask, what is the mean waiting time? What is the average time a message is unread? Okay? And well, you can do the math, and you'll get that this equals 30 minutes. Okay? So it's a pretty straightforward thing, okay? Or you can say, if you don't understand this, but you can say I have mean arrival to 12 an hour, and I can tell you the mean waiting time for a message is 30 minutes because the total time is 1 hour. So on average, you're going to wait 30 minutes. Then I can plug these two, and I can tell you that on average, I have 6 messages in the queue. Okay. In fact, every time I observe it, it will have 12. Okay, but on average, there were 6 in the queue. So if I take any random point in this interval and I sample the number of messages in the queue, the number I'm going to get is 6. Okay, so you can kind of use it either way. All right. Any questions about this over here? So this is again, this is just giving you a simple explanation of why we have this kind of situation here. All right, let me pause here, and we'll take another application of Little's law and then derive it before we go on to stochastic processes. Okay, any questions about this over here? Relates these two quantities, the mean number of customers, mean waiting time. Let me try and use it for a practical example. And again, here I'll show you how we can use queuing theory, or in this case, Little's law, for kind of approximate seat of the pants kind of analysis. So let's say that we have a web server. So I'll put the parameters here as before, and I'm going to just go with the numbers here. Okay, so I have lambda equals, let's say it gets 10,800 requests an hour. Okay, now you'll say, well, which hour, right? Obviously, web servers are going to be busy sometime and idle sometimes. All of the analysis for what's called teletraffic systems. By the way, if you want, you can sit here, because there's a seat over here. On any of you guys in the corner, because you can't see this presumably. Okay, you can come there if you want. Anyway, so we take what's called the busy hour average. So what you do is you measure the system, and you find the hour of time that is the most heavily used, and you look at the busy hour. And so this you can do it for the busy hour. So whatever time, it could be 9 a.m. or 5 p.m. whatever. So we want this 10,000 requests an hour, and this corresponds to, of course, to 3 requests per second, which is why I chose that number. And the second thing we want to know is that we want the mean waiting time less than or equal to 6 seconds. Okay? So, all right. Why do you want it to be less than 6 seconds? Again, there's a very influential study that was done, I think around 1997 or 98, which said that people wait roughly 8 seconds for a website to come back before they, just say, well, I'm giving up. Okay, where they either do retry or they just stop. So if you are providing service as a web server, your e-commerce site, whatever it is, if you can't give a response back at the server in 6 seconds, you need about 2 seconds, roughly for network latency, then you can't beat the 8-second rule. So if you are an IT manager in a company or a .com or whatever it is, you're running a company website, you're going to be almost surely being told, make sure the mean waiting time is under 6 seconds. It's an important parameter, okay, because 8-second rule comes in. And so what you want to do is, what should be the longest queue length? Okay. In other words, when the queue length gets beyond this, then you're going to say, server is busy. You want to send back whatever the 303 or whatever number is that says server busy, try again. Okay? Because it's better for you to say busy, try again, than to just have the request go off into nothingness. So we'll use little sort to analyze it. Well, what we want over here is that the mean waiting time should be, let's say how long it takes to be 6, and we have the mean arrival rate is basically 3. Okay, so we get right away that the mean number of customers is going to be 18 at this arrival rate and at this waiting time. Okay, so in other words, if you want to bound the waiting time to be 6, okay, so this is the mean, right? If we set the buffer size to be 18 requests, it means at 18 you say that you're going to have server busy, signal being sent out, then what you're doing is you're saying that the max is 18. Okay, of course, we just want the mean to be 18. It's still okay, so this is conservative. Okay, all right? Because if you said that the max is 36 or 40 or whatever, you would still get a mean of 18. That would still be okay. But I'm saying the max is 18. Then so now you get a sense of how you do this ballpark sizing. Okay, so you find out the number of requests per hour. You know that. You can do that from measurements. Management tells you, or your HCI people tell you 6 seconds, then you say, okay, I'm going to use Little's law. I come up with the mean to be 18. If the mean is 18, what should the max be? I don't know. It really depends on the arrival process. Okay, it could be 18, it could be 100, it could be 200. But if you have to decide, you can say, well, we'll be conservative. We'll say server busy at, let's say, 20, and you'll still be okay. You'll meet the management guidelines. Maybe too conservative, and you can then start fine-tuning this. But at least you know roughly what's going on. And that comes straight out of Little's law over here. Okay? Any questions about this so far? So the mean number of customers is, of course, the number of requests that should be allowed into the system before you say, all right, too much, go away. Okay? So if you apply this to Tim Hortons, if you knew the mean arrival rate, which I guess you could, and you want to bound the total amount of time that you have in the system, you can say, well, no customer should wait for coffee more than, let's say, 3 minutes. Then that will tell you how long a queue you should have, and you could paint a red line on the floor. It says, if you see this red line, go away, because your waiting time will be too long. And some places actually do that. They have a sign on the thing that says, waiting time from here to service is roughly 30 minutes. So we want to discourage you from being, or you pick up the phone, right? Sometimes you get this call that says, the time to service is expected to be, whatever, X number of minutes. Well, how did they get that? Well, they got that from Little's law. Okay, they know essentially the waiting time, they know the arrival rate, and they can guess what your number of, so you have the number of customers, the mean arrival rate, you can kind of get the numbers out of that. Okay, so how do we prove Little's law? And there are many different ways of proving it. I'm going to show you a proof which is correct, but has a little bit of mathematical sort of trick inside it. And I'm going to leave you, maybe somebody will figure out the trick, maybe not. But I'm going to show you the proof with the trick. The proof without the trick is much more complex, and I didn't want to do it. So I'm going to tell you the proof with the trick, and let's see if you figure out the trick. If you cannot figure out the trick, try it later on. Okay, so what's the proof? What we do is we look at a time period of duration small t. Okay, that's our time period. And I'm going to tell you how many people arrived in this time period. Okay, so how many people arrivals in this time period is nothing more than lambda t. Okay, and let's, you know, the mean waiting time, we know that, that's just capital T. So the total amount of waiting time of this cohort of arrivals, right? You have this kind of group of people, I paint them all red, and I'm going to say, okay, how much time did you guys wait? Okay, total. Well, the total waiting time for this set, well, it's nothing more than lambda t, right? Because these are the bunch of people, and they each waited on average capital T seconds. So the amount of, you can think of this as customer seconds. The amount of customer seconds of waiting time is lambda tt. Now let's do the same computation a slightly different way. Okay, number of, or it's a mean number of customers in the queue equals n. That's just notation. I'm not doing anything special over there. Now, okay, let's just think about it. I have mean n customers in the queue, all right? Let's say 1 second elapses, okay? 1 second elapses, all right? How much mean waiting time overall did I incur, right? I incurred n customer seconds of waiting time, right? So how much total waiting time am I incurring in small t seconds? So the waiting time incurred okay, for over t seconds is nothing more than nt. Well, that's basically got to match the waiting time incurred for this cohort of customers, because this cohort of customers is no different from any other set of customers. The mean is the mean is the mean, right? The waiting time incurred for this guys has got to be the same. So we get lambda t equals nt, and cancelling t out, we get lambda t equals n, which is, of course, a little slow, all right? So all I'm doing is I'm computing the total amount of waiting time incurred in two different ways. One, by looking at the time period duration t and how many people came and sort of how much they incurred. And the second thing is I'm sort of saying, well, this is how many people are in the queue, and obviously over this much period of time, I'm going to incur this much time. I can just equate the two, and I get a little slow. So this is a mathematically correct proof. There is something slightly funny going on, and I'm not going to tell you what it is. But anyway, try and figure it out. All right, so this basically proves what it is. Now, of course, it tells us that this is independent of the time period considered. We actually don't care what this time period of t is. It just pops, just goes right away. And all we care about is this. And again, this whole argument, this whole proof, does not depend on the arrival rate or the service rate or the arrival pattern, the service pattern. It's just completely independent of all of those things, which is why it's powerful, and it's why it's very widely applicable to all queuing systems. Okay. Any questions about this over here? Okay, so let me move on to the next one. This actually gets to be one of the most fun parts in this work, as far as I'm concerned, because I'll explain why. Okay, so stochastic process. So when you start talking about queuing theory, the first thing you come across pretty much is the concept of a stochastic process, and it's one of the most confusing concepts for students. You know, you kind of say stochastic process, I don't know what the heck it is. And I had the same reaction. It's like, oh no, you know. Why? Because the definition of a stochastic process is defined as a family of random variables indexed by time. Okay, great. What the heck? Where do I start with this? Doesn't make any sense whatsoever to say I have a family of random variables indexed by time. And that is a mathematically correct definition, and I'll explain to you, and it's now 12:20. By 12:35, hopefully you'll understand what exactly it means very, very precisely. So I'm not going to skimp on the math, but I'm going to explain it to you in a way, hopefully, that you understand exactly what this means. And if you understand stochastic process, if you understand intuitively what it is, you'll understand queuing theory. Okay, so it's very, very important for us to do this. And the reason is because stochastic processes are the basis for our description of the arrival and departure processes from a queue. So we want to show you how people arrive into a queue and show how people depart. And the interaction of arrivals and departures, of course, is transient process of queuing. It comes in, it goes away. It depends when you arrive and when you depart. So understanding stochastic processes is very, very important. So let me explain what it is using the following example. So imagine that there is a staircase. Okay, there is a staircase somewhere. And let's say it has 10 steps. I'm not drawing all 10, but there's 10 steps. And there's a big clock next to the staircase, and the clock goes tick, 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 like this clock right here. Okay, so that red arm kind of moves around, and every second goes tick. And let's say there's a person standing over here on some stair. Let's say the person is on stair number, let's just number these 1, 2, 3, 4. Person is on stair 2 at time, let's say time 0. And what happens is this person can climb stairs in 0 time. Okay, just assume they can climb stairs in 0 time. So when the clock ticks 1, they're on step number 3, right? And then clock ticks 2, they go on step 4, etc. Right? So each time the clock ticks, they go up, right, like that. So I can ask you the following question. I can say, okay, suppose the person was at let's just make it easy, at time 2. He's on step 2. Where is he at time 20? Where is he on time 20? Right? Anybody want to answer this? In step 20, right? This is absolutely obvious, right? On time n, he's on step n, etc. So this is straightforward. Why is it straightforward? Because it's a deterministic process. It is not a stochastic process. Deterministic process means that we can predict the future exactly. Okay? So if you think of this, instead of people coming up the queue, we have people coming into Tim Hortons. At time 1, the first customer arrives. Time 2, the second customer arrives. Time 3, the third customer arrives. So I can tell you, what time does the 50th customer arrive? So time 50. No big deal. Okay, now I'm going to make it a bit harder. Okay, not very hard, just a bit harder. Person is standing on stair 2, and what that person does is he tosses a coin. Okay, let's say he tosses a coin, and if it comes up heads, he goes up here, and if it's tails, he comes down here. And if it lands on the edge of the coin, he stays there. Okay, so there's some non-zero probability of staying anywhere, but he goes up and comes down. Let's just say these are 0.5 and 0.5. Okay, it's not a very complicated problem at all. I'm standing here, person standing here either goes up the stairs, 0.5 probability, or goes down with 0.5 probability. Now I say at time 2, he's at step 2. Okay, this is deterministic, and this is with a half kind of thing. Where is he at time 20? Sorry? Why is he at step 2? Really? I guess you didn't attend the lectures on probability. Try again. Anybody else wants to try again? Where is he at step 20? I'm sorry? He's at 10. Why is he at step 10? It's a Gaussian distribution. Okay. Not exactly. It's not Gaussian. It's a binomial distribution. Okay. So it's actually not even binomial, because he at 0 he kind of has to. So it's a binomial. It's a kind of funky binomial, right? It's a binomial that is upper and lower bounded. So it's a binomial with reflection, and you don't want to go there. Okay. The answer is you don't know. Okay. You only have a probability over all possible steps that he could be at time 20. Okay. So let's get this very clear. Deterministic process. Okay. If I tell you this and I tell you the rate at which he climbs steps, I know where he is. Step 20. Got it. No problem. Here, with just a simple change in rule, which just says make a probability going up and down, I can tell you that in expectation, most likely he's still on step 2, okay, perhaps. Okay, maybe Usman, that is what you're trying to say, that your peak of the expectation value will be at step 2. That's actually not true necessarily because he's very close to this end, okay. So he's got some other probability pushing him up. Maybe his 3 is most likely. I don't know what it is. You have to simulate it and find out. But the important point, the only point I want you to understand is this. I don't want you to determine the probability distribution. What I understand is I really don't know. I only know that there is a distribution over what? Over these steps, right? I have some probability of being here, some here, some here, some here, but I can't tell you precisely what it is, okay? It's very similar to Tim Hortons, right? A mean arrival rate, which corresponds to the stair climbing rate, is, let's say, 1 a second. I'm going to ask you how many people came in 10 seconds. I don't know. I don't know. I can say the possibility that 5 people came is this, the probability that 6 people came is this, probably 7 people came is this, etc. I can give you a distribution. What is this a random variable of? Okay, if I represent the random variable xi as being the probability distribution at time I, okay, what I'm looking for is what is the probability distribution at time 20. That is what I'm asking over here. And clearly it's a random variable. It's distributed over a domain. What is a domain? The domain is the number of steps. Okay? Okay. And so let me drive that point in by actually doing a little bit of computation. Okay? So let's say at time 2, this guy's at step 2, and let's just use the same thing. So basically, we have probability half of going from step I to I plus 1, and probability half of going from I to I minus 1, except at stair 10 and 0, right? At 10, you basically, let's say you go down with probability down to 9 with probability 1, and at 0, you go, or 1 to 2, you go up with probability 1. Okay, I'm just kind of making this up over here. Okay? All right, so let's find out what happens. So at time 0, I know for sure what the fact is. So at x0, I can say has the following distribution. x0, the probability that x equals 2, let's just say time 0. Probability that x equals 2 equals 1. Okay? That's what I told you. It was at time 2. Time 0 is at step 2. So that's x0, probability x equals 2 is 1. What about x1? Okay, now what is the probability that he's going to be at step 3? What's the probability he's going to be at step 1? Okay, so we can write that down. Probability that x equals 1 equals a half. And I can say probability that x equals 3 equals a half. And I now have a discrete probability distribution, okay, which essentially describes what x1 is. The random variable x1 is a discrete random variable, and its domain are the two values 1 and 3, and the probability of having this value is half, and probability of having that value is half. Okay? Well, let's just continue one more step just to make sure it works. So what's probability that, what is the distribution of x2? Okay, has some probability that x equals 1, right? So what's the probability that x equals 1? Okay. Well, we can look at the path. So this guy came down. If he came down, the next time around, the probability of being 1 is what? At time step 2, what's the probability is going to be at 1? What's that? Anyway, it's not a trick question. It's very simple. It's 0. It's 0 because obviously I told you that he's going to 0 to 1. He's going to go 1 to 2. So probability that he's going to be x equals 1 equals 0. What is the probability that x equals 2? Well, it depends. So if he came down, they went down with half and he's going to come back up. So I get at least a half. And then with half he goes up and comes down again, so there's 1/4. And that's only two ways you can come back to step 2. So it's 3/4. And then probability that x equals 3 is what? 1/4, because this whole thing has to add up to 1. Well, actually not. half of going up again, and then I can say probability x equals 4 equals 0, right, and so on. 4, 5, 6, etc. I never got there. Okay, so I've shown you explicitly the distributions of x0, x1, x2. And you can see you can compute x3 and x4 and so on this way. Yes? Why is it to 0? Oh, I'm sorry, right. 3 is, so he's going to go up, or that's right, yeah, so I take it back. You're right, it's 0. 4 is 1/4. Thank you. Yeah, that was a mistake. Yeah, thanks. So, but the point I'm trying to make here is I can compute these. Each rule is deterministic, right? The rule that I have over here, or at least the rule for computing probabilities, is deterministic. Okay, so the rule, it's probabilities, but at least I can compute them. Okay, and I'm giving you an example of this, and I've made some hidden assumptions which I'm going to unhide now one by one to show you what's actually going on. But at least I want you to get the following important thing. I have a distribution for x0, which is a trivial one. I have a distribution for x1, I have a distribution for x2, and essentially for xn, let's say x20, which is the question I started out with, where is he at step 20? That is nothing more than x20. And now I've shown you a process that allows you to compute the distribution for x20. You don't need to say it's binomial or this or that or the other. You can actually compute it explicitly, sort of step by step, by just plugging this into an Excel spreadsheet and kind of just clicking on it, right? It's going to give you the values. So what do I have here? What do I have here? I have a set of random variables. I don't have one random variable. I have x1 is a random variable, x2 is a random variable, x3 is a random variable. Each of these is a random variable. What are they indexed by? I. What is I? I is at time I. So what I have is a set of random variables that are indexed by time. And what was that? A stochastic process, right? So this is really what's going on in a stochastic process. A stochastic process essentially is a system or something where the future depends on the past, but it does in a way that is probabilistic. In other words, it's like somebody flipping a coin to go here or go there. Okay? And so when you look at the process and we want to figure out what happens in the future, I can tell you probabilistically what it's going to do by assigning a distribution to that appropriate random variable corresponding to that state in the future. However, I don't know for sure. I only have a distribution about the future. So this is why the mathematicians call a stochastic process as a family of random variables indexed by time, because that's exactly what we have. Here is a family of random variables, and sure enough, they're indexed by time. So this is a stochastic process. Okay? And I want to point out one more thing about stochastic processes that's very important. And that part is that in stochastic process, we can think of, something moving. Okay, what is moving? In this case, I actually drew a person. The person is moving. Okay? Well, what's moving in a stochastic process? There's nothing moving per se. We talk of the process moving. Okay? And what we actually say is this. We say that the process has a trajectory until some point in time. So what is the trajectory? Let's say the time now is 2. Okay? Now I have a probability distribution over x2. I have probability distribution x2, but I observe the guy, I say, hey, time 2, you are on step 2. I have, for example, an observation that says the process, or more precisely, the random variable x2 equals 2. Okay, and by extension, random variable x1 has a value and x0 has a value, right? So I've told you what x0 and x1 and x2 are. So I know the past exactly. I can view that if the current time is 2, I know the past exactly. All right? Now what I can do is I can say, what is x3? Okay? Well, I can use a computation similar to this that says if x2 is known, because here I started out, if x0 is known, I can tell you what x1 looks like. And here I said if x1 is known, I can tell you what x2 looks like. If x2 is known, I can tell you distribution of possibilities for x3. And of those possibilities, one will be chosen. let's say x3 equals 3 is chosen, okay, we talk of the stochastic process as having moved from value 2 to value 3. It's like the person over here moving from step 2 to step 3. There's no person. It's just that x2 equals 2 is known, and the next value, x3 equals, let's say 3, becomes known at time 3, and we view that as moving from 2 to 3. And what are 2 and 3? These 2 and 3, the steps that I've been using over here are what are called states, okay, the state variables. We can think of the stochastic process as having a domain, okay. In this case, the number is 1 to 10. And what we say is that the variable corresponding to a particular point in time, let's say x2, chooses a value from the domain, that is, say, 2 or 3 or 4 or 5. And what happens is the trajectory tells us what are the values for prior random variables. Okay, these are not random anymore. These are not deterministic, because it's the past, right? And we figure out what is the distribution of the next point in time, like x3, and the next 2 points in time, x4 and x5 and x3. So we can think of, if you want to look at it this way, we have time on this axis, and I guess is what we're using over here. And let's say I'm looking at this point in time over here. So I have some trajectory, I can go up and down and so on. I have some trajectory. The future, I have all sorts of paths, potential paths. And at any point in time in the future, I can tell you the distribution over these paths. For example, if x2 equals 2, then x3 has a value of 10 with probability 0, okay, or 9 with probability 0. I'm telling you distribution. So I can tell you the distribution of the future. The future is unknown. The past is known. The trajectory is known. And when the time step advances, we pick one value. We choose this path. We go over here. At this point, this trajectory is known. The future beyond this is also unknown. Okay? So you've got to keep it straight in your head that in a stochastic process, we have determinacy for the past history, but the future is not known. And we can only tell you the distribution of the future, which is exactly what I said over here. At time 2, you're in step 2. That's deterministic. At time 20, I don't know the future. I have to kind of run through my math and compute these distributions over here. At the end of it, I can tell you this is the distribution of probabilities for these values, the domain, which is numbers 1 to 10, at time 20. But I don't know exactly where it's going to be. I can tell you distribution. Okay, any questions about this? Yes? Is the transition function deterministic? Question is the transition function deterministic? The transition function, in this case, is deterministic, right? In other words, the transition function is exactly this one over here that tells you to go from I to I plus 1. In everything that we'll study, the transition function is deterministic. I can write down a rule that tells you, given the value at x at 1 or 2 or 3, this is the next set of possible states that's going to take. That rule itself is deterministic. Okay, now you can make it, you can come with all sorts of variations, but yes, it's deterministic. The distribution of values of the stochastic variable is probabilistic, but the rule is deterministic. Right. Any other question? The question was this: is this rule probabilistic or not? Okay. In other words, I can toss yet another coin that tells me the probability that I'm going to go to the next step. Okay. I can kind of think of this doubly stochastic process where I don't even know what the rule is. Even the rule itself is a different stochastic process. So I can actually build up doubly and triply and whatever. A stochastic process gets more and more and more complicated. But we're not doing that here. We're saying the rule is deterministic, but the random variable is stochastic.
Transition between states?
Yeah, between states. The probability of, basically what is the probability that x equals, let's say 3 conditional on x equals 2? Okay, is this rule deterministic or stochastic? Okay, and this one is deterministic in this case. Yes, question, yeah.
Even if you have several layers of non-stochastic processes, can't you collapse them all into one deterministic transition function?
In some cases, yes. It can get very messy. So for now, let's not worry about it. Okay, we'll just worry about this one, or just with this one over here. Okay. Yes.
Will the time and the states always be discrete?
No. After the break, we'll talk about continuous time, continuous space, and so on. Those are the types of stochastic processes. Any other questions? Okay, I guess I should take a short break to refresh your brain for a second, and then, because if you want to get to the talk at 1, we probably should stop here. Okay, let's take a short break, and I will continue with these processes here so far. So the notion of having the staircase and so on, and the person moving, was to try and make concrete certain things. Okay, and I want to concretize over here 3 things. The first thing is that we realize that the person has got to be in one of the steps. Okay, the set of steps is finite, and we actually will call these states instead. And we can think of this as the domain of the random variables. In other words, the probability distributions are defined over the states. Okay. The second thing I want to talk about is the clock. That's sort of the time. We'll still call it time. And we have our clock basically ticking off time, and we have movements coupled to this ticking off of time. So that's still the same. In a stochastic process also we think of time as going past. The third thing is the person who's moving. There is nobody there. There isn't anybody moving. Okay, there isn't a stochastic process person jumping from state to state in some funny game of hopscotch. No. What we have is, we essentially have that the trajectory, okay, chooses samples. Okay, and I'm going to put down this term over here called sample path. And let me just draw this over here. So we have some distribution of, or some, not distribution, some history of prior states chosen by the corresponding random variables x0, x1, x2, x3, x4. And after this, we have a set of future trajectories or sample paths. And what happens is that, let's say the probability of being at, at this value something, probably being this value something, probably this value something. Well, we'll flip a coin, a bias coin, pick one of them. We pick that. That is a sample, right? After that, it becomes history. And then after this, we get the future again. So what we get is that each instantiation of a stochastic process, all right, each instantiation of a stochastic process gives us a sample trajectory, which is sampling from the space of all possible trajectories. Okay, so we have this kind of infinite possible set of trajectories, and a particular instantiation of this is a particular sample path through this space. And what we claim is that this sample path is representative in some fashion of the entire stochastic process. For those of you who have done simulations, this should sound pretty familiar. Okay, what do we do in a simulation? We have some deterministic state as of now, and we always have a source of randomness. Okay, typically in a Monte Carlo type simulation or any simulator, we choose some things from certain distributions. We say packet arrivals follow whatever pattern, and service rates follow this pattern, and with this probability is centered on this link, or other probability is centered on other link, whatever. We choose randomness from certain number of elements, and we can view the entire state of the system as being some random variable, and then what we get is trajectories, sample paths through the simulations. And these sample paths are stochastic. Okay, when viewed, I mean, they're not deterministic paths. I can't tell you what the simulation result is going to look like until I run the thing, because it's stochastic. And this is why when we talk about statistics, we'll come to this. This is why we do simulations. You have at the end essentially a random value. Okay, a random value meaning that it's a value that is the end result. At the end of your simulation, you end up somewhere over here. That is the end. That is chosen from some distribution of possible endpoints. And you've got to express the confidence with which you are actually choosing something that is, So when you say, my simulation tells me my queuing delay is, 30 seconds, well, guess what? That's because you chose a particular set of intermediate random values. It could be 35, it could be 32, it could be 22, whatever. So if you see a paper and somebody says, here, this is the value I got is 30 seconds, and only has one simulation run, it's complete garbage. Okay, this person has no idea what they're talking about. Similarly, if you do an experiment, right, we talked about pipettes and dropping water, dropping reagents into bottles and so on. Each step of that can be viewed also as a stochastic process. Okay, you have some random. When you say I'm going to get 5 milliliters, actually I may not get exactly 5 milliliters. I can get 4.9 or 5.1 with some distribution, and then I drop it in. Maybe some particles, were blown away by the wind and fell off somewhere else. So the final results I get also can be viewed as being the value of some kind of stochastic process. And again, what I'm saying here is that what you got at the end of it is just one trajectory, okay, and you have a bunch of different trajectories. Okay, so this is a very important concept. If you want to really understand what's going on when you do a simulation, what's going on when you do an experiment, all you have to remember is that this is a stochastic process. It is not deterministic, and therefore the outcomes are also not deterministic. Okay, to come back to this, now let me try and give you a certain amount, very simple categorization. Well, over here I have steps. Okay, so I have step 1, step 2, step 3. What I can say is that this is a discrete state system. Okay, that's steps. All right, and I also have discrete time because I have a clock. It means move on clock tick. We can make both of these continuous. It's very simple. How could you have a continuous state system? Okay, does anybody want to, in this context, what would a continuous state system be? That's right, a ramp. If I were to take a ramp, I can say, okay, you can move any infinitesimal you want, up or down. So you can move up or you can move down any infinitesimal amount you want. That would be a continuous state system. And how about a continuous time? Anybody want to? Sorry?
Move at any time.
Any time, that's right. Continuous time just says ignore the clock. So in the discrete state, discrete time, I've got to be on a step, or I should say the stochastic process is such that the random variable assumes values from a discrete domain, and in the continuous state, it assumes values from a continuous domain, in other words, from a real interval. In the discrete time, we can think of integers as representing time, 1, 2, 3, 4, etc. And in the continuous time, what we have is something slightly more complicated. In continuous time, what we have is a set of time instants, t1, t2, etc. Actually, it's infinite, where these times represent the time at which the transition occurred. Okay, I'm going to repeat this because it's a bit complex. In the discrete space to continuous space, it's easy, right? We just say it's a ramp, you can move any infinitesimal amount. In continuous time, it's not like you're saying that you can move at any time. Yes, you can move at any time, yet you move only at a particular time, right? In a particular trajectory, you chose to move at a particular time. You didn't move at all times. Okay, so if I look at the past history, I can tell you that in the past history, you took this long T1 to move to the step. This one was T1 plus T2. This one is T1 plus T2 plus T3, etc., where the Ti's are the inter-movement times. So the trajectory is indexed in some sense with a set of time instants, and these time instants are the times at which actually it's not T1 plus T2, just T2. The gap, this is T2 minus T1 is what I really want to say. This is T1, T2, T3, and so on. So the time instants when you moved are those, and the inter-time distributions could be, Poisson or whatever, exponential, whatever it is. It doesn't really matter. But in continuous time, we associate a set of discrete time values, the times at which the transitions actually happen. Transition meaning that the random variable x, whatever it is, xt, acquired a deterministic value at that point in time. That's when the transition happened, right? When this kind of probability distribution collapsed and became a single value, that is when we say the process moved into that particular state, okay, which could be a discrete state or whatever. So all four combinations are possible because obviously I can have discrete states and continuous time. That means, I wait on this thing and it can go up and down anytime I want, or I can also be in a ramp and it can move up and down arbitrary intervals at arbitrary points in time. So it gives you continuous state and continuous time. Okay. Let me see if I left out anything over here. Are there any questions about this at all? Okay. So, all right. Let me see. Yeah, I think I'm pretty much all I wanted to say. So now what I want to do is to tell you a little bit about where things can go wrong. All right. So let me suggest, let's study the simplest possible case, which is discrete state, discrete time. So you're back to being on a step and a clock, and you say, okay, that sounds pretty easy. I'm going to tell you that it's not easy. It's actually quite complicated. Okay, so let me just show you why it's complicated. So here is what I want to do. Remember, I can make the rules as complicated as I wish, so I will make them complicated. Let me just draw the steps like this, and let's just consider step number 5, for example, and I'm just going to tell you the following rule. Okay, if you arrive to 5 from 6, then your next step is going to be step 3. And if you arrive to 5 from 4, your next step is going to be, let's say, 6. And if you arrive from anywhere else, then your next step is going to be, let's say, 1. Okay? Why not? I can make that happen, right? I can certainly say that. I never said you can only go up and down one step. You can certainly make you go multiple steps. So here is the problem. I say, okay, I see the guy and the person is on step 5. Okay? Say, what is the next step? Where is the next step going to be? Well, I don't know. It depends. It depends on where that person came from. If the person came from 6, I can say it's going to go to 3 with probability 1. It comes from 3, etc. 4 goes to 6, and otherwise it goes here. So if I know the past history, of the trajectory, I can tell you precisely the distribution for the next time step. I can't tell you the exact value. I can tell you the distribution of the next time step. Okay, so I can tell you the probability that xi plus 1 equals some value k, okay, given xi minus, given xi equals whatever, let me call it xi, just to confuse you, xi minus 1 equals xi minus 1, xi minus 2 equals xi minus 2, x0 equals x0, where you can see that the small x's represent values from the domain, in other words, values from 0 to 9 or 1 to 10, whatever, and capital X's represent the history of past values of the random variables, because I know that at time, what I could think of as time I know this entire history. I know the value at I and I minus 1, etc., etc. All right? And I can give you this distribution, Pxi plus 1 equals k. What am I saying over here? Because I know that in the previous step he's now at 5, he was previously at 3, and so on and so forth. I can make accurate predictions of the probability distribution for xi plus 1, the random variable xi plus 1, right? But it's messy. It's messy because I've got to keep track of the whole past history. What if I did this? I said that I'm going to exclude certain stochastic processes. I'm going to exclude all those processes where history is important. I'm going to have a stochastic process with very, very, very limited memory. All it knows is the current step. All right? So if I say that this must equal xi plus 1 equals k, given xi equals xi. Okay, in other words, I know the current value of x, so small xi. That's my current state. And I can tell you about the distribution of the next value of the stochastic process. And of course, from this, it means all future as well, because I've completely ignored past history. In other words, not allowed. You can't do that. Okay, so I'm ignoring this. If my process has this property that I can describe it accurately using this, I call this a Markov process. This is called the Markov property. Which means no history. Or to be more precise, everything you need to know about the history is encapsulated in the current state. Okay? If I know the state is whatever I equals 5, then, or not I equals 5, xi equals 5, then I don't care how I got there. I just need to know the guy was in step 5, that's it, the future is known. Okay? In this case, we call this a Markov process, and we can define similarly a Markov property for continuous time, which I'll do it later in a different class. But I want to just pause here and say, okay, does everybody get this? Because this description of a Markov process is extremely important. Okay, it's extremely important that you understand what is meant by no history or memorylessness. It means that given the trajectory and given the current state, I can throw away everything in the past history of the trajectory. I just need to know the current value of the random variable, because I just need to know this one. And then conditional of this, I can tell you the entire distribution for xi plus 1. Okay, and so on, because I can tell you the future. But the another way of putting it is the future depends on the past only through the current state of the stochastic process. Any questions on this? Okay. Because this is like the most fundamental thing about. So you need to understand what is meant by stochastic versus deterministic. You need to understand what a trajectory is. You need to understand the notion of a family of random variables, and now a family of random variables where we are going to essentially have no history, and that's a Markov process. Okay? Yes?
So Markov process can also accurately predict xi plus 1 as the stochastic process could accurately predict knowing all history.
That's right. So Markov process is a stochastic process also. Right? It's just that it's a stochastic process where we can ignore all of this. Even if we didn't know all of this, we would still make accurate predictions. In other words, just make an observation that at time 5, the state was, step 5, discrete value, so it was on step 5. I don't need to know where it was before. I don't need to know in the past, whereas in the example here, I did need to know where I need to. So it is a subclass, but it turns out to be, in fact, a very, very important subclass of stochastic processes, and it shows up all over the place, okay? And therefore, it's, as I said, it's one of the most important concepts, and talk about, so that's Markov process. And let me stop here. I'm going to just say one thing, which is that I realize that it's quite important, as you get into the more mathematical concepts, to start doing the homework as you get them. So I actually put up the homework assignment already for queuing theory. I would encourage you to try solving the numerical examples there for this lecture, before the next lecture, because if you can't get this in your head straight, you're going to be in trouble next lecture, because next lecture we get into quite a bit more math. So solve the homework examples, and yeah.